All right, looks like we're ready to go. So we'll just carry on with chapter 10 tonight. We got largely through 10A yesterday. And so I think we'll probably be completely done with it tonight. I was having an issue opening up Blackboard a minute ago. Oh, here it is. Okay, I think we're good. So let's see what's in here. So there's two parts to 10, 10A and 10B. So 10A is largely but not completely done. And if you remember, we left off with our discussion about matched pairs. It's a special type of hypothesis test. And then what's going to happen in 10B is we're going to focus our attention on not two means, but two proportions. Okay. Um, Hold on. This thing is being very stubborn. So once it lets me get all the stuff open, we can get started. There we go. Okay, so let me get those open. Okay. So yeah, like I said, 10B is for proportions. We'll get to that in a bit. First, we have one last case to consider when we're comparing two means.
Oh, Professor,
Yes.
you told me to remind you about the Excel.
What about the Excel? I forgot what I was supposed to remember.
You said about the students who can't get the Excel T and C tables. You would do it.
Oh, yeah, you have to,
The data pack.
the data analysis tool pack. That's it. That's it. So, if you can't get into it, because I'm starting to realize that there's multiple versions of Excel floating around, which I wasn't aware. It didn't used to work that way. There was like Mac version of PC, that was it. Now there's also these variations that are coming on the internet. Some of them are based on Google, some are not. And so they don't always line up with each other. So I think what's going to have to happen is, unless somebody has an answer for that, because technology is absolutely not my thing, I think I'll just have to maybe have people send me an email and say, I'm one of the people who cannot download data analysis tool pack. And then that way, I'll just make a note of it, and then that will have to do it for your assignments. So the ones that do require it, well, I can't require you to do it if you don't have access to data analysis tool pack. So I don't know what else to do because I have no idea who I would call or speak to about this. If I could be there and look at your computer, it might be a little easier, but even then, I'm not sure I would be able to fix it. Um, Theoretically, all versions of Excel should have data analysis tool pack. The Macs have a slightly different version, or at least I believe they do. They have something built in there called Excel Miner, which is basically the same thing with a few extra features. I don't know if you have a Mac or not, but I don't know what we can do about this, if there's anything we can do. Um, so, like I said, I'm going to have everybody who has this problem send me an email, and I'll add it to my roster. And so that way I'll know those people are not expected to hand in the assignments that require data analysis tool pack. I don't know what else we can do about it. It's so, I mean, it's really just a small percentage of the grade anyway, but I don't want anyone to be penalized because the technology is failing them. So it only really affects a handful of these Excel spreadsheets. It will not affect your mind taps because if they need data analysis toolpack, they've actually built a version of it into MindTap. It'll give you whatever you need to take care of it. Okay. So if somebody discovers something, let me know. But I don't know if there's anything else that could be done about it. Okay. So all right. Anyway, let's get back to this. Uh, So let's scroll down. So we started, I don't think we actually started the problem with the matched samples. I just started to show you what it means. Okay. Yeah, here it is. Why don't we start here again? So here, the basic procedure is exactly what we've been doing, except that the samples themselves are related to each other in some important way. And so we cannot use the other techniques we've been using in this chapter. Like all statistical procedures, there's always a bunch of assumptions going on behind the scenes. And up to this point, everything we've done in chapter 10 was based on the assumption that the populations we were studying were independent of each other. But that's not always the case. So we need to know what to do about it if the populations are not independent of each other. And so here's our first case. It turns out, though, that this approach is actually a little bit simpler than what we were doing before with that horrendous degrees of freedom formula. And so you'll probably be happy to see how straightforward this really is. So they're giving us first this case where we had workers completing a project with two different techniques. And what we're looking for here in that last column is the differences between them. And we're trying to find out if there's any difference in the completion time between the two techniques, and which is equivalent to saying, is the difference between them equal to zero or not? Okay. So the notation is slightly different in this section too. They usually, instead of writing mu1 minus mu2, what they're having us do is replace that with mu d for difference. Okay. So it reminds us that ultimately what we're interested in here is not the individual population elements, but the differences. Okay. I think that's probably why they set it up this way. And so they start by showing us that in this case, if we want to compare the two directly to each other and see if they're equal or not, then we have a two-tailed test here, and this is what it looks like. Okay, so this is our two-tailed test. And of course, we also have the option of doing a right or a left-tailed test. We can still do that. And they're just exactly what you would expect. It'll be our right-tailed test. You can tell because the null hypothesis, the alternative hypothesis is pointing to the right, so to speak, or in other words, the critical value would be in the right tail of this distribution. And of course, I'm sure you can guess what's coming next. The left-tailed test. All right. And then we have this really strange looking test statistic based on the t distribution. Already there's a difference. It's d bar instead of x bar because that reminds us that we're looking at the mean differences minus the hypothesized mean difference. And then instead of the standard deviation, sample standard deviation, we have this standard deviation of d. And then down here, we divide by the square root of n. That part hasn't changed. That's the sample size. So now these are the standard deviation in particular could be very time consuming. So I showed you a special technique with the calculators that would enable us to do this directly without too much work. And it involves putting our differences into the lists. So when we do our first example, we'll do exactly that. So what do we have here? So this is the one with the workers. And actually, I think we already did put this into our list last night, didn't we? Let me just double check. It will still be there. It doesn't erase itself. If you go to lists, you can find them by hitting stat. And it's going to, wait a minute, whoops. Now, when you hit stat, it's got three menus to choose from. The one we want is the one that it is already set to. And not only that, but we want this first entry one. So in other words, you're already there. You just have to hit the enter button. And so what you'll see is all these lists, L1, L2, L3, all the way. And so what you're going to do is first erase everything that's in L1 if there is something, and then you'd put in the numbers, which in this case is zero point 0.6, negative 0.2, zero point 0.5, zero point 0.3, 0, 6. Okay, if you did this yesterday or last night, it'll still be there. And then what we discovered, or I showed you, is that if you hit the stat button again, and this time instead of edit, you scroll over to the calc menu with the arrow key. The one on top is the one we want. And that's going to, oh, and by the way, when you get to that point, you're going to have to tell it where your list is, a list of data. It should say list one. You can ignore the frequency list. If this is not L1, type second one. Okay, if you look carefully at your keys, directly above the numbers in blue, at least on mine it's blue, it says L1. Okay, for two, it's L2. So in other words, to get to the list, you hit second and then the number you want. So if you do that, it'll say L1. So you can go ahead now and go down to calculate. Of course, hit enter, and all the details are right in front of you, of which we only need two of them. What it's calling X bar is what we're calling D bar, 0.3, and what it's calling SX is what we're calling SD, which is 0.33, 466 approximately. Okay. And now you actually have enough information to finish out this test statistic. So we'll just plug it in. See if I can copy it. So we have D bar is 0.3. This is equal to 0 because we're trying to find out if the two procedures equal each other. It would be up here. We actually are using the two-tailed test in this case. And then SD is it's about 0.33466. And we can divide by the square root of n, which is 6. Now, here's an important detail. If you notice, there's 6 in each sample. So n is 6, not 12. On top of that, each sample has to have the same number of observations, otherwise this doesn't work. Okay, so in other words, you couldn't have 6 of one and 7 of the other. Now, if you pop that into your calculator, Your test statistic will be approximately 0.2. Close enough. We usually round that to two digits. And then, of course, we can do one of two things with that. We can find the p-value, or we can look up the critical values. Let's see. Now, they didn't do that. Let's do that for ourselves. Let's start with the critical values. And for this test, um, for two-tailed, it's going to be plus and minus t alpha over 2, n minus 1 is the degrees of freedom. Okay, nice and simple. So then we have right tail. Left tail, just the negative. Okay, so I believe in this case, alpha was 0.05. So we have t with 5% in the right tail, 5 degrees of freedom. Okay, so that's going to define our rejection region. Now we can look this up in the calculator by using INVT, which stands for inverse of the t distribution. And it's going to ask you for only two things, the area and the degrees of freedom. And of course, as always, the area means the left tail. So if the right tail contains 5%, the rest is 95%. All right, let's see what that is. Yeah, I did something wrong. Here we go, 2.015. All right. Since the test statistic is 2.2, that of course means that we're in the rejection region and we reject the null. Acceptable alternative that it is different from zero. Now, if we decided to use the p-value approach, the test statistic is what determines the p-value. 2.2 in the right tail. So this is our test statistic, and this defines the boundary for the p-value. So what we need to do here is look at the probability that t is greater than or equal to 2.20, which we can find in our calculator, second vars, 6 TCDF, and it needs lower and upper, and degrees of freedom, which is 5. All right, let's see what that is. 0.0395. And now remember that we chose an alpha 0.05. So therefore, P is less than or equal to alpha. And as you recall, that means reject the null. And accept the alternative. So we notice it gives us the same results as the test statistic critical value approach. It has to. Okay, so that would be your classic example of a matched pairs problem. And we will do this in Excel, but I want to do it by hand first. Let's see. That's better. I can now see everything. Now, by the way, this diagram is taken from a book. Before calculators became as powerful as they are now, what did people do to solve these problems? Well, textbooks would come with enormous tables of results. And this is probably in the back of our book somewhere, but we don't really need it. The problem with that is that with the t distribution, at least, it can only carry so much information. And so we often find ourselves needing to find numbers that are in between other numbers. It was kind of a headache. So, but that's what they're showing us here. So you don't have to worry about this part because we're using our calculators. Okay, unless you enjoy using old-fashioned technology. All right, so here's the Excel. Maybe later on we'll get back to that. I'd like to carry on instead with something new for now. But you can see this one does require the data analysis tool pack. So let's go on to part B, where we introduce hypothesis testing for two proportions. And just a quick reminder, the book uses P for the population proportion. First, let's remind ourselves what we're doing here. So in the book, they're using P for the population proportion, sample proportion. Make sure the notation is clear. So we'll start with the confidence intervals. This is our standard error. It's a bit of a mess, but we can do it. That will, of course, be an integral part of our formula for the confidence interval, as well as the test statistic for our hypothesis test. And again, assumptions, there's always assumptions. These conditions are required to be met for our results to be meaningful. I mean, anything else, the numbers start to get less accurate. So they probably will ask you about this in Mind Tab. So if they do, this is what they're talking about right here. Let's see if I can copy this. It's giving me trouble. Doesn't seem to want to work. All right, you know what? I'll just write them down. You can see they're both the same. So because there's two populations here that we're studying, we need four conditions. Those are the ones we technically should meet before we do this test or do this confidence interval. Failing that, your results will be less reliable. So, it's good to be aware of these conditions. Okay. And here's the confidence interval. And I would like to point out that, well, this looks like all the other confidence intervals. This is my margin of error. And this is my point estimate. All right, let's take a look at a first example. Tax preparations. Okay. A tax firm is interested in comparing the quality of work at its two regional offices. We randomly select samples of tax returns prepared at each office. We verify the accuracy. And of course, they're trying to find out if the proportion of errors is the same at both offices. And so here's the data we have. Office one is, all right, now N1 is 250. The number with errors, we're going to call that X. Whoops. 35. And so P1, the sample proportion, is the ratio of these two numbers. Whoops, sorry. Okay, that is the sample proportion from Office 1, 14%. Well, that sounds very high, doesn't it? That's a lot of errors for tax returns. No, well, I don't know. Maybe they're counting everything, like even if there's a spelling error in the address or something. Office 2, all right, here we go. 300, 27, and that's going to be 9%. Now, that looks like a significant difference, but it's hard to be sure without doing a formal test. Okay. So that's what we're trying to find out. We're trying to find out if the two proportions are equal. Okay. So But first, we're going to do the confidence interval. Let's get this formula back. And so I think we have, oh, it's, what is it, 5%? Yeah. Right. Let me confirm that. It is 5%. Oh, no, sorry, I misunderstood. It's 90% confidence. See, what they're saying is that construct a 90% confidence interval. Now, remember how this works. When they tell us a confidence interval, that actually means this equals 90. If you divide, you'll see that with a little algebra, alpha is 0.10, which of course means that alpha over 2 is 0.05. And we're looking for the corresponding z-score for 5% in either tail. So really all we need is this number here because the other one is just the negative of that. And the same thing could be said for the negative. If you'd rather solve for that one, that's fine too. How would you find it? You'd go to second vars, um, 3 I and V norm, and it's going to ask you for area. And remember, always look in the left. But here, since we're already in the left tail, you just put 0.05. Sorry, 0 and 1, because this is the standard normal distribution, or Z, the Z or standard normal. And when you go through all that work, fine, it's going to come up as a negative. Um, and this one we usually round it to 3 places. And so since that's the negative, that means this one, so this is the one that's going to go into the formula. Okay. Not, it doesn't really matter actually, because you're doing plus and minus anyway. All right, so let's do some substitutions. Remember, P1 is 14. 2 bar is 0.09. 14. Now, of course, 1 minus that is 0.86. Ah, I forgot about the sample size. So let's go look those up. N1 is 250, if I remember correctly, and N2 is 300. Yes, good. that just a little neater. And now we solve. It's kind of a mess, but we can do it, right? So now obviously this is 0.05. That's easy. All right, I'm getting a standard error of approximately 0.0275, but it's still, of course, the margin of error requires us to multiply by that 1.645 over here, 0.045. So it's going to be, right, so yeah, and that's what they got. Beautiful. So I'm sure they're going to have us do a hypothesis test next. Okay. Yes, we'll get back to this in a bit. Now we're going to do the actual hypothesis test. And of course, you can see exactly what's going on here. There's left, right, and two-tailed. These are not written as differences. We're just doing P1 minus P2. Only the matched pairs case has the mu d with it. Here, the rest it's always written as one minus the other. Okay, so might as well write them all down. Once again, the left refers to the alternative hypothesis because it shows us where the rejection region is. Then the right tail test. Doesn't matter what order you write them in, but I like to do it this way because you can see clearly the right tail test means the alternative is that the difference is positive, and then this you could just put whatever's left over. It helps avoid confusion, I think. And then two-tailed test, of course. So here it's either they equal zero or they don't. All right, that's all there is to it. All right, let's see what they've got for. Oh, yes, yes, yes. We need this. So it's getting a little messier. Yes, that's true. This this one is used if you believe that the two populations have the same proportions, you can average them out with this statistic. And in some cases, you will need this. We'll see how that goes. But it'll pop up for certain cases. So just be aware that this means P bar is the average of P1 and P1 bar and P2 bar. So it's a weighted average of the two because the sample sizes are not necessarily equal. For all that, here's our test statistic. Now, by the way, I just want to mention this right up front. When testing hypotheses about proportions, unlike with means, where we might use the t distribution, or we might use the z, here it's z only. Actually, this is true for one proportion too. I'm just going to write proportions, just in general, whether it's one or two. We only use the standard normal distribution. Or z. All right, t would never show up in a case like this. So you don't have to make any decisions. All right. So there's the tax firm. We want to test the hypothesis that the error proportions differ between the two, which means that it is a two-tailed test using the 10% level of significance. Alpha is 0.10. Um, oh, look at this mess. Now, if you notice, this P bar does show up in the formula. So we're going to use it right now. Let's do that first. But let's also go remind ourselves what the numbers look like. Um, Here we go. Okay, so let's do the P bar first. So we'll plug in the numbers. So, and remember, N1 was 250. E1 bar. What I just noticed that when I copied it, let me just see something here. These are supposed to have bars over them. Yeah, I don't know if I forgot to put them in, but there's supposed to be bars over there. Yeah. Anyway, so let's get back to without the bar, it's a population measure, which we don't obviously observe. So yeah, same thing here. These are supposed to be bars. All right, so now we can do this. So we have point 14. Let's find out what that equals. All right, it's approximately 0.1127. That's close enough. Okay. Now, with that in place, we can do this nightmare. And the two are 14.14, 0.09. So one minus that is 8873. Then we have 1 over 250. I'm running desperately low on space here. Maybe I could move it. All right, so plug that into your calculator and see what you get. Whenever it's a real mess like this, you might want to think about simplifying it a little. This part is what I'm thinking about. 1 over 250 plus 1 over 300 is approximately 0.0073. All right, I think this will be a little bit more manageable. So I've got 185 as statistic. I always breathe a sigh of relief when you solve for a messy expression. Now, of course, I can do two things. I can do a p-value or I can do a critical value test statistic. So let's look up the critical value. Uh, L test. But remember, alpha was 0.10. It's often 5, but it's not always. Here it was 0.10, so keep an eye on that. Of course, that means alpha over 2 is 0.05. And of course, we did this for the confidence interval, and we discovered it to be 1.645. So this is my rejection region. Of course, the test statistic we just calculated is 185, which puts us out here. Reject the null and accept the alternative that the difference is not zero. And had we chosen to do a p-value, test statistic was 185, but we have a two-tailed test here, which means we need both tails. So everything outside of the p-value, a test statistic is the p-value. So here it's these two pieces. So we need both of them. So we can actually just look up one of these and double it because they have to be the same due to the symmetry of the distribution. So if you go to normal CDF, I'll just randomly pick the one on the left. So we have negative infinity up to negative 185. But of course, there is no negative infinity in here. So we type negative second comma 99, and that is replaced with negative E99. These stay at 0, 1. It's about 0.03 to 2, let's say. But then remember, we have to double it. Okay, now the alpha was 0.10 though. So therefore, p-value is below alpha. And of course, that means reject the null. Oh, sorry, proportions. What am I doing? And of course, again, as always, they're the same thing, the same result we had up here. Okay. Okay. That didn't seem too bad. Okay. So now that means we can go ahead and just do those Excels since we finished 10B. And let's see, which ones would those be? Yeah. Okay. So if you go to Brightspace, I'm sorry, Blackboard, you'll see it there. There we go. In chapter 11, 10 rather, we've got, I think it's three. So they are down here under chapter 10. You'll recognize them right away when you see them. We have checking account. The phrase with annotations. Oh, I think we've already done this one. That looks like we did that one. Tax prep, that's new. Oh, I wonder if I made a separate one. Oh, you know what it is? This one is the confidence interval. And the one that follows is the hypothesis testing case, right? So that way we know which is which. We have a software. Oh, no, we did this one already. Exam scores. We did that one. So that leaves the matched. This one we haven't done. All right, let's get them open. All right, so I think we should do the match pairs first because that came in 10A. This one, yeah. See, now, unfortunately for some of you, you won't be able to do this. Here's what you have to do. Um, Matched. Okay. Remember the workers with the two different methods. So, as far as Excel is concerned, you're going to go to Data Analysis Toolpack and pick t-test paired to sample for means. Matched or paired, it means the same thing. So let's do that. Data analysis, um, paired. That's right. So this is variable one, this is variable two, and be sure to include the headers, but then also click on the labels. And if you want it on a new sheet, you can. It defaults to that. You can leave it right here if you want, but then you have to make sure it doesn't override the data. So you could, for example, put output range F1 tells it to start at F1. And there it is. Be aware you'll probably have to widen up these columns. I don't know why this keeps happening. And we remember we rejected this one. So we had our p-value way back here, procedure, and the p-value turned out to be 0.395 for a right-tailed, no. Um, I think this was meant to be a two-tailed test. I don't remember the way the question was worded. I see right tail, so I guess this is was a right tail test. But anyway, these are the three different p-values. This is the one we got, and this is what it would have been with the two-tail test. So that's it. This one is done. So save it and send it to me. Uh, then we came across that should be it for 10A. 10B, this thing we did was, I believe, a confidence interval. Yeah, the tax office is okay. So this one is set up for us. It's all the information is there. So we're going to follow along with their logic. Um, this one. I just want to put a, here it is, here it is. So the sample size, now of course, this means that they intend for us to do these parts for ourselves. So in other words, there's a lot of data here, by the way, and they're not the same. Remember, it was 250 for one. Also, remember, these are alpha. This is not numerical data. So when you count, you have to use count A. Now, if you don't want to scroll around over here, here's a little shortcut. I can find the bottom of this column, at least on the PC, by simultaneously holding down Shift, Control, down arrow key. See, it's at the bottom. Let me make a note of that in here. As you can see, sometimes it'll come in handy. Shift, Control, and then down arrow. This keyboard, the down arrow is this key. It's way down in the bottom right. Simultaneously, that is. All right. Anyway, so close the parentheses, hit enter. Then we have to do the same thing for Office 2. Count A. If you do count, it'll just give you a 0. Oh, yeah, there's that little trick again. Responsive interest. Now, remember, um, okay, so we're looking for the yeses, but don't type it, copy it. Because otherwise, if it's not absolutely identical, including all the blanks, then you will have a problem. Now, count for response. Let's go back and see how they handled that. Oh, they did count if. Okay. So actually, let me make this a little bigger so you can see it. Yeah, that's better. So in other words, count if, meaning go through the entire column, and if and only if you find yes, which I'm showing you in cell E6, count it. Otherwise, don't. Then over here, you're going to say count if B2 through B301, and then also refer back to this cell, F6, and it'll tell you how many of these had a mistake. All right. So now sample proportion is a ratio of these two numbers. I can now drag across. In case you missed something, I'm going to do the special command that lets you see everything all at once. What did I do there? Another Excel tip. The key, it's control plus this little key, which is actually known as tilde. You'll find it just to the left of your one key. This shows all formulas. F2, now this one is a little trickier because it depends on the keyboard you're using. F2 shows um, the formula in cell on the PC. I think um, Control U works on the Mac, but this is secondhand information. You'll have to confirm that. So let's get this back where it belongs. Confidence coefficient. I think this one was meant to be 90%. So just literally type 0.9. Level of significance is 1 minus that. 1 minus this number. And over here we have 1 minus this number. And then the z-value, or the critical value. This is a little tricky. It's done a little differently than the calculator, but you'll get used to it. You're going to type equals norm dot s dot inv 1 minus open paren level of significance over 2. Okay, let me just show you one more time. And so basically what it's saying is the left tail, if you've got a 10% alpha here, we have to cut it in half. So you're looking at 5% in either tail. But remember, we always want the left tail, so this is telling it to look in the left 95% tail. This one, you can drag it across. Now, by the way, remember I told you that we're going to round this to 3 places? Look at all those digits. If you would prefer to see it as a rounded number, up here, you see the two commands, increase and decrease decimal. Here I want to decrease. And whoa, it looks beautiful. Now I can do the same thing here, but I'm going to show you another trick. If I want to copy a format from one cell to another, I choose the one that I do want. You hit this little format painter and touch the cell that I want fixed. And there it is. Look, Amazing. All right, now the standard of error is everything in these in the square root here, so that's going to be a mess. Wow. So let's see if I can shrink this up a bit so I can see it. Maybe we can do this. So square root is SQRT. We'll need two sets of parentheses, P1 bar times open 1 minus P bar, P1 bar is here. Might need another set of parentheses. 2 times 1 minus P2. God. It's a miracle I did it. All right. I'm going to show you. I'll make it bigger. Nightmare formula that I just put in there. Wow. Oh my God. All right. So I'll give you a minute to get that all down because it is kind of a mess. Okay. So let's finish this up. That by far is going to be the worst part. I mean, there's no way any of the other formulas are anything close to that. Margin of error, remember, is the product of the z-score and the standard error. And the point difference of the estimate is the difference between the two sample proportions, 0.14 minus 0.09. And so now the lower limit is this point difference of the estimate minus the standard error. I'm sorry, the margin of error. And then here, it'll be this number plus. Oh, we can reduce these to something more manageable. So we have the confidence interval. Now we have to do the actual hypothesis test.
Sorry,
Sorry.
for the margin of error, what was the formula?
Oh, yes, let me show you.
Thank you.
All right, no problem. Did you want to see anything else?
I think I'm good. Thank you.
Okay. Yeah, I mean, if you're getting these numbers, the rest must be right. So yes, that's done. But tax prep also has the hypothesis test. That would be the last one for tonight. So here it is. And it's the same data. Now we're actually testing the hypothesis. So again, remember how to do this. The sample size is count A. And I'm going to start here. And let's say this is a lot of data. I don't know where it ends. Shift control down arrow, close the parentheses, enter. On this side, it was count A. Select over here, shift control down arrow key. Now I see I'm typing the right parenthesis and I'm hitting enter. It's bringing me back more or less all the way to the top. But here's the bottom line. That's how this part works. Then see the rest of it, this is exactly what we did. As a matter of fact, I'll tell you what, let me show you a helpful hint. Since everything is literally the same, unless it's in, ooh, oh boy, I just realized something. No, we're good. It's since they're in the same rows, we can save ourselves a little time by copying these because they're referring to the same exact data. As long as everything's set up the same way, not a problem. Yeah, there you go. Well, that's a nice time saver. Now, for this one, hypothesized value, I think they mean the zero difference. Let me confirm that. Yeah, they just mean zero. Point estimate of the difference, though, is the difference between these two. Oh, you know what I just realized? I don't need both of these because, yeah, it's different up here. We have data for both offices. These are numbers that are common to the entire problem. I think. Let me just confirm. I want to make sure. Sometimes the wording here is not as clear as it could be. All right, that part is right. Oh, you know what I just noticed? There's a typo here. This shouldn't say point estimate. It should say pooled estimate. Oh my God. Yeah, that's why I was confused. That's this thing. Uh, okay, so I only just noticed that now. There was a typo. Instead of it said point estimate, it's supposed to be pooled estimate. This is the hypothesis testing one. 13. Okay, so let's figure it out right here. All right, it won't be that difficult. N1 times P1 N1 times P1 plus N2 times P2 is N1 plus N2. All right, I'll make this a little bit bigger so you can see it better. That's this thing over here. Oh. Well, good. Now, standard error was another nightmarish formula. This one. Let me just copy this. When they say standard error, they mean the denominator here. So it's going to be square root p bar, which is this one, times 1 minus p bar times one over n2. Sure, I got all the parentheses lined up. Oh, all right. So I don't think I calculated that separately here. But anyway, this is what I got. And then the test statistic is the numerator is very simply P1 bar minus P2 bar. Simply divide by the standard error. And yeah, that's what we got. Now for the p-values, for the left tail, norm dot s dot dist, we're going to calculate the probability of being 5, 6. So you'll put E15 1 for cumulative. For this one, norm.s.dist. This one you put 1 minus norm.s.dist. And then for the p-value, they have this weird approach of their own. Remember, it's like 2 times the minimum of these two or something like that. Let me just go look. Let them have that. That works. So put 2 times min E17 comma E18. So it's the double the smaller of the two. Well, all right then. If you've gotten to this point, you can send that to me. So that would be 3 altogether, 2 tax preps and the matched pairs. That was everything so far. So I think we won't do any more Excel tonight. We're going to start chapter 11. And 11 is just like all the others, all about hypothesis testing, but maybe a little bit different than what we've seen up to this point. There could be some exciting twists in what we're about to see. Okay. So I don't want to keep you in suspense. Let us go open chapter 11. So, by the way, you're now ready to do all the assignments for this weekend, which involve 9 and 10 only. Then I believe the following weekend is either just 11 or 11 and 12. So I'm going to go find, God, I have so much stuff open. 11. Only one chapter, or, one spreadsheet, sorry, slide, PowerPoint presentation, but, ooh, it's a doozy. Let's get that open. Oh, there's a chat. I hope it hasn't been there for half an hour. Yes, just send it to my email. My email address, just in case you forgot, is yeah, because you know what? Theoretically, there's a way to post it on Blackboard, but I, I've had it done, but I just don't remember how it works. It's one of those things where it's just not worth the trouble. So here it is. Anderson6 at fordham.edu. So don't forget that 6. All right, so finally we're ready for chapter 11. Now 11 is really is different than 10. 9 and 10 were very closely related to each other. This is a little different. It's not that we're not doing hypothesis testing, but it's a different kind of hypothesis testing. In other words, it's not the mean and it's not the proportion. And because of that, we're actually going to need to introduce not just one, but two brand new probability distributions in this chapter. And unfortunately, we don't have all the functions in the calculator that we would like to have for these. So we're going to end up at some point having to use the ancient technology, the table. Okay, so we have to learn how to use the chi-squared. Well, the name of the distribution that we'll start with is chi-square. We're going to use its table, and then the second one is called the F distribution, and we'll need to use its table as well because those functions, sadly enough, are not in here. I guess they ran out of space or something. So what's different in this chapter is instead of testing hypotheses about the mean or two means or proportions, instead we're focusing now our attention on variances. So we're going to first test hypotheses about a single population variance, and then we're going to do the same thing for two variances. So now the problem here is that the variance itself does not follow the normal distribution or the t distribution. So therefore, we need something else. Oh, and of course, we'll do confidence intervals and hypothesis testing. So we're going to start by introducing our new favorite distribution, and it's called chi-squared. So chi is actually a Greek letter. Let me show you what it looks like. It's basically a fancy X. It's spelled CHI, but it's pronounced as if you were saying Chi. Don't ask me why. I'm not a scholar of ancient Greek languages. Not even close. And so what you'll find as we move into the more intense and more complicated probability distributions is that often they're related to each other. And what happens is in statistics is we're trying to ultimately our overriding goal is to be useful. So results are chosen or derived with that in mind. And so what happens here is that if you take a series of standard normal random variables, let's write this down here somewhere. Remember, this z it represents a random variable specifically chosen from the standard normal distribution. A random variable simply assigns numerical values to the outcomes of an experiment. If I were to take a series of these, that sum gives me the chi-square distribution. And down here, I'm writing an n. The n represents degrees of freedom. So the chi-square distribution has its own version of degrees of freedom. So this is where it comes from. Now, based on what you're seeing here, there's some implications of this. One of which is that the chi-square distribution does not allow for negative values. You're summing up squared terms, and therefore the sum can't be negative. And if I were to draw a picture of this distribution, what would it look like? Well, that does depend on the degrees of freedom, but in general, this is more or less what it would look like. See, it starts at zero, and it's not symmetrical, is it? It's skewed to the right. Uh, the other things we notice are that the chi-square distribution is continuous because it's constructed from a continuous random variables. So this, in other words, remember in stats one, you learned about discrete distributions like the Poisson and the binomial, where the number of possible outcomes of an experiment was finite. Here, these are the continuous ones with an infinite number of possible values, including the normal, the t, and now the chi-square. Now, one thing we do want you to see is that the shape of this curve depends on the degrees of freedom. So I think they have, yeah, here we go. They're helping us out with this. They're showing you that 2 degrees of freedom, it looks kind of weird over here. It doesn't have that nice mountain look to it. 5 degrees of freedom is this one, and then all the way over here is 10 degrees of freedom. So if you notice, as we increase the degrees of freedom, the curve is stretching out more and it's also getting flatter. Okay. So the shape will ultimately depend on the degrees of freedom, but they're always going to be continuous and they're always going to have be skewed to the right. So I think that's all. Now, I did mention that the calculator doesn't have the function we need to calculate chi-square probabilities. So I'm going to show you right now the table we will be using. It's hiding out in Blackboard. In chapter 11, you'll see it here. It's called, well, what do you know? Chi-square table. Give it a minute to download. It's still messing around with us. There we go. Now, they have a nice little graph there. You can visualize what it's doing. But here's one of the quirky things about this table. We've been harping on this business about left tail areas all this time. Every time you go to your TI-84, you're looking for the area, maybe a critical value or whatever for the t or the normal. We're always looking in the left tail area. The chi-square distribution, it's the other way around. We have to get into the habit of looking in the right tail because of the way it's defined. So what you're seeing on the top are the alphas, the different alphas. And over here on the left column here, you're seeing the different degrees of freedom. And, of course, they can't cover them all, but they've got a large percentage of them. So to look up a value under this curve, we need the right tail area and we need the degrees of freedom. So they have an example here at the top. Let's say alpha is 0.01. That would put us over here. Oh, I forgot. This is PDF. I can't write on it. Um, so 1, but I can highlight it. And for 4 degrees of freedom, which is here, intersection of those two is right here, 13.277. So let's draw that on the notes. Everything's blocking each other's view here. This is not good. Especially this table for some reason. I can't see anything down there. Here we go. And then we have, so the example was, what was it, 4 degrees of freedom. So the entire curve is a result of it being 4 degrees of freedom. In other words, there's one curve for each degrees of freedom. And the tail area that they're looking for is 0.01. So we're way out here in the right tail. Whatever that is, it represents only a tiny slice. So how do we find it? Again, look at the intersection of 0.01 with 4 degrees of freedom, and you'll see that it's 13.277. Now, I would like to point out here, though, that the values under the chi-square distribution can get very large. Why is that? Because you're adding up squared values. They're typically much larger than for the standard normal and t distribution. The way it's constructed, you're going to get much larger values than you're used to seeing. So 13, you'd never see that in the standard normal. Are you kidding? That's so far out in the right tail that probably you wouldn't reach that once out of a million years or something. It's a rare event. Okay, here it's different because it's only 1%, 99% to the left, 1% to the right, because the chi-square distribution is a sum of squares. All right. So keep this table handy when you're doing these problems. Oh, I think here we go. So this is actually good practice. This is where we're splitting up the area into 2 tails. So let's say that they've decided to construct a confidence interval. We'll see how that's done later. Alpha is 0.05. Alpha over 2 is clearly 0.25. And let's say that we have doesn't say the degrees of freedom. Let me just see if they mean for us to keep it at 4. No, that wasn't. Let's look at the table. 8.907. There it is. Wait a minute. Maybe I can draw. Oh, wait a minute. What do we have here? Yeah, that's weird how they didn't specifically tell us what degrees of freedom to look for. And then 32.852 would be here. So that means obviously they forgot to tell us that this refers to 19 degrees of freedom. So they'd like to know the values that form the boundaries of these points under the curve. Oh, look what I'm doing. I'm drawing the normal curve. I got to break that habit, that's for sure. So we need the 2 points such that this area is 025. So is this. So the way it's written, now remember, everything's geared to the right tail here. So, oops, what am I doing? It means that over here, 0.975, because everything to the right of that is 0.975. So when I go to look these up in the table, I need this value here and the degrees of freedom at 19. So again, we'll go back to the table with 19 degrees of freedom. Can't seem to find the table. Oh, that was it right there. I went right past it. Right. It doesn't matter. So for 19 degrees of freedom, to find this value, I'm going to look in the column headed 0.975. So if you go to the top, it's right there. 8.907. Now this one has a right tail area of 0.025. So that's the column heading I'm going to need. Here we go. 32.852. So think of those as critical values. They separate, in this case, the upper 2.5% from the lower 97.5%. Of down here, we separate the lower 2.5 from the upper 97.5. So if I'm constructing a 95% confidence interval, I will need these values in the formula. Yeah, well, we'll get used to it. Don't worry. It sounds a lot more complicated than it is. But if you notice, with a normal distribution, uh, let's say a 95% confidence interval of something like this, 2.5% in either tail. Here's the symmetry ensures that these two numbers are the same, but with different signs. I lose that with the chi-square distribution, so I have to look them both up. Okay. So we have to keep an eye on that. We have to look them both up because they're not going to be equal to each other. All right. Well, what else do we need to know here? This the horrible looking formula is how we're going to find confidence intervals with a population variance. That was we just looked up in the table. Wow. And now also let's not forget that n is the sample size. And then S is the sample standard deviation. That S squared, of course, is the sample variance. All right. So let's see if they've got an example here for us. Oh, by the way, if for some reason they want a confidence interval for the standard deviation instead, then you would just take square roots. In other words, remember the variance is the standard deviation is the square root of the variance. So, I mean, it makes sense that all you would do is take the square roots. So, I just want to mention that here. So, do they have an example for us? Oh, yeah, there it is. They did it. Here we go. Liquid detergent process, a product filling process. The filling mechanism for the process of filling a liquid detergent is adjusted so that the mean weight is 16 ounces per container. Now, normally that would be a huge deal. It's an important number, but here we're going to test a hypothesis, or actually, we're going to construct a confidence interval for the variance. Um, this is a very strangely worded problem. They have a sample of 20 containers, and then they finally, in the next page, get around to telling you that the sample standard deviation is 0.0025. Yeah. But they also want us to know that if the sample variance is excessive, we'll adjust the mechanism. That means that the amount in each bottle is not consistent. But that also tells us that this is a right-tailed test. And so they're aiming for Oh, I see. No, that comes next. They want a confidence interval. All right, so let's ditch this approach. Now you recognize those numbers. We just looked them up in the table. This is what we're actually doing. All right, so remember the sample size is 20, so this becomes 19. S squared 0.0025. And so what really separates the two terms is that here we have the chi-squared alpha over 2. That is found in the right tail. Well, actually, that's the other thing we got to watch out for. There are no tails as such here. So, the terminology is a little different. So we have instead chi-squared alpha over 2 is the right critical value. The other one is the left critical value. This is 32.852. And over here is the 89907. And so then you've got to calculate this with your calculator. So if you plug those in, the one on the left is 0.005, let's say. On the right, 19 times 0.0025 divided by 8.907, about 0.00533. And, if we really were interested in the standard deviations, although it doesn't ask us to do this, you would take the square root of first 00145 out 038 on the right-hand side, square root, and it's about 0.073 by taking the square roots. Okay, what else did they? And again, there's some Excel. Now, here's the hypothesis. So let's just quickly look at how this works. It's the same setup as what we're used to seeing, except that we're looking at variances. That's all. So here's what our left tail test looks like. Right tail test. And the right tail means, uh, it refers to the alternative hypothesis. And of course, our friend, the two-tailed test, right here. Okay. And then, of course, they have to tell us what the test statistic is. And you'll see it looks surprisingly simple. N minus one. Look at that. Look how easy that is. That's it. Yes, it is. At least for this case, it's very simple. And also, then we don't forget about the critical values. Is it separately? Yes. So for the left-tailed test, now it's easy to get tricked with this. One minus alpha. If this would be alpha here, this is one minus alpha. If alpha, for example, is 0.05, then that means we're looking at a right tail of 95. Okay. The right tail test, so this time alpha is in the right tail. Okay, that's our critical value then. And for the two-tail test, as always, we split the alpha in half. We just don't have symmetry to take advantage of. Oh, whoops. Oh no, that's right. These both have the shaded region is still alpha over 2. That hasn't changed. But they have them all listed here. So the part the when you run this test, you're still looking for the test statistic, whether it goes into the rejection region or not. That part hasn't changed. The p-value hasn't changed either. In other words, a small p-value means you're going to reject. A large p-value means you will not reject. Okay, so um, so let's run this real fast. This won't take very long. We're being told that the St. Louis bus company wants to make sure that people think they're reliable. So they want to know about it if the bus drivers are not arriving within 4 minutes of the scheduled time. They're worried that it's too large, and that means the buses are not arriving in time. So this would be a right tail test because we're looking for evidence that the variance is above 4. That is where it becomes unacceptable. And they'll make a change. But if not, then everything will stay the same. Alpha is 0.05, I believe, yes. So our friend, the test statistic is, hold on one second. Now, what else are they telling us? Um, the sample of 24 buses is taken, and the sample standard deviation is, oh no, sorry, oh, this is a typo. This should be S squared, 4.9. Right then, so let's plug in these numbers. The hypothesized variance is 4 right here. So our test statistic is, oh, by the way, since the calculators don't have what we need, we're not going to be able to do p-values here. Uh, yeah, I know we like p-values, but 28.175 and the critical value, given that it's a right tail test, is, oh, that looks helpful. So keep in mind, here we have 23 degrees of freedom. And the tail area is meant to be 0.05. So now here's the unfortunate thing about the chi-square. There's already a superscript. So unlike with the t where we put degrees of freedom up there, there's no room. So what I would usually do is write it like this. That way they're both visible at all times. I like this notation. How easy this is to find. You go to your table, you look for the column headed 0.05, which is this one, and 23 degrees of freedom. Let's see, 35.172. All right, and of course, as usual, we're looking for evidence that the test statistic is too extreme. But the test statistic was 28.175, which does not land it in the rejection region. So we do not reject the null. That the variance is less than or equal to 4, and that means no changes need to be made to the bus driver schedules. That wasn't so hard, but it just takes some getting used to the way the chi-square is different than what we're used to seeing. Right, and so you can see what happened there. Now, what they're doing is they're they're kind of doing a p-value. What they're doing is they're basically grabbing a point in this table they have, and they're giving you a range of values for the p-value. They're not finding the actual p-value, but they're giving you a range. Um, I don't think you'll even need to do that. Now, we don't want to go any further here because, first of all, we want to do the Excel, but not till next time. Secondly, um, they're jumping right into the two variances, and this one requires another new distribution, believe it or not. So I think it might be a smart move. By the way, that's it for chapter 11. So, it's complicated, but not long. So we're in pretty good shape time-wise. In fact, we're quite a bit ahead of where we have to be, I think. So that's good. So anyway, why don't we knock it off here? As usual, I'll post all of this good stuff. The video, of course, goes on my YouTube account because of the lack of space and Blackboard. And then I'll put the notes that I've been taking on Blackboard, so you'll have both of them. And when you go into MindTap this weekend, see what you're going to be confronted with. Now, keep in mind, this is a very, very compact course. So you should assume that something's due every weekend, especially since the 4th of July is over now. Um, yeah, we got some cranking to do here. Now, having said that, if you're having issues that are making it hard for you to get your work done, like let's say your boss is making you work overtime, or let's say you're on vacation, or let's say you're not well, or anything like that, just let me know and I can always give you an extension. Oh, here we are. So here's what you need to do though. When you go into MindTab, make sure you look at the right menu to see what's due because they've got a lot of stuff in there that we have not assigned. And so you don't want to sit there doing every one of those little practice problems that they have. There's tons of them. All right, let's give this a minute. The net has been a little sluggish tonight. Well, that's as sluggish as it gets. Anyways, so let's say, oh, here it is. This right here, this is the menu you want to be looking at. All right, let's get this out of the way. The one that looks like a little calendar. So you can see this Sunday, the 12th. Oh, I see a lot of you have already done it. Good. So I don't honestly know how long this is going to take. I've heard conflicting things about how their estimates are too high, they're too low, but it won't be a trivial amount of time. So don't start this on, 10 o'clock on Sunday night. And keep in mind, you're allowed to work on this in stages. You can do a little here, a little there. You don't have to wait until you can do it all. And also don't forget, you get 3 tries for each problem. It'll keep the best one. Now, the one thing that hasn't happened, I'll probably get this ready over the weekend. We're going to have our exams online using MindTab, but they're not in there because they're not written yet. I have to work on those. Um, I haven't done Stats 2 with MindTap during the summer before, so that's why I need to sit down and write them. But, I'm going to set them up so that you can start them whenever you want to. In fact, all of them are open as we speak. So if for some reason you wanted to jump ahead, there's nothing to stop you. I get people sometimes who ask, like, can I start right away? Can I jump ahead? Fine. And it's set up, they're already open. If you think you can do it, that's fine. But of course it's not necessary. And then the exams would come down here somewhere. And it would be just like the same thing, only more questions. Okay, so everything's going to be done online, except for the Excel, of course. And the semester is going to go fast. So keep that in mind. So but we're making excellent progress, um, in my opinion. So, yeah, we know we're really zooming it here. Well, that's better than falling behind, right? So, all right. Anyway, I guess we'll stop right here and I'll see you tomorrow. Okay.
Thank you.
All right. Good night.
Thank
Thank
you.
you.
All right, bye.
Thank you.
Professor,
Yes.
how many Excel sheets are we sending in today? Three, correct?
There were just the three. Yeah.
Got it, got it. All right, thank you so much. Have a good rest of
All
your
right.
day.
All right. See you next time.